the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video in a series on least squares problems for linear algebra students. In this video, we're going to talk about the normal equations and how to solve least squares problems using those normal equations. So without further ado, let's go ahead and jump into a definition. The system of equations A transpose AX is equal to A transpose B is referred to as the normal equations for AX equals B. Now, you may say to yourself, wait a second, what's the difference in these two? You just left multiplied by A transpose. And you're absolutely right. That's all I did. Left multiplied by A transpose. But there's something very special about the normal equations that you see here. And I call them normal equations in plural because technically it is a system of equations. And so there's more than one equation actually hidden behind the scenes here. They are often pluralized for that reason. And as a notational note here, the solutions of the normal equations are often denoted by x hat. Now, if you just watched my video on the concept and definition of the least squares solutions, you likely know that that has something to do with the solution to a least squares problem. And I should possibly pluralize when I say the solution, I should say the solution or solutions to the least squares problem. And we'll see why that's important in a little bit. So why are the normal equations so important? I mean, it's just taking the equation AX equals B and left multiplying both sides by A transpose. What's so big about that? Well, let's recall that if you have a solution to the least squares problem, and we call that solution x hat, so in other words, if A times x hat is equal to the projection of B onto the column space of A, and just to remind you what that looks like, we have this vector B right here, and we wanted to solve AX equals B. However, it turns out that the column space of A is that pink highlighted region. Therefore, A times any vector X will never generate the vector B. There's just no solution to that equation. It's an inconsistent system. But as we mentioned in the previous video, we can get an approximate solution by finding the projection of B onto the column space of A. And then instead of solving AX equals B, we solve AX equals the projection of B onto that column space of A. And that's what we're going to do here. So going back to why are the normal equations important? Well, if x hat satisfies that AX equals the projection of B onto the column space of A, then the vector B minus that projection is going to be orthogonal to the column space of A. And again, we wrote that right here. That blue vector is B minus the projection of B onto the column space of A, and it's orthogonal to the column space of A. Well, what the heck does that mean? Why is that useful? Well, that means that if A sub I is a column vector of A, so A sub 1 be the first column of A and A sub 2 is the second column of A and so on and so forth, well, then that column vector dotted with B minus the projection of B onto the column space of A, that should be 0 because those two vectors should be orthogonal. Remember, A sub I is a column of A, so it is a vector in the column space of A, and B minus the projection of B onto the column space of A is orthogonal to every vector in the column space of A. Thus, the dot product of A sub I with that orthogonal vector, well, we know that a dot product is just the transpose of that vector times the orthogonal vector. And we could rewrite a little bit here. We happen to know the projection of B onto the column space of A just by what we set up above right here. The projection of B onto the column space of A can be rewritten as A times x hat. So we'll go ahead and replace this notation right here with just A times x hat. Well, and we know that dot product has to be 0. So therefore, A transpose times this vector B minus AX hat must be 0. Well, A transpose, that is a row. And by the way, that should be A sub I transpose, not A transpose. Sorry about that. Let me write that in here. But A sub I transpose, well, that's the ith row of the matrix A transpose. And if I tell you that the product of the ith row of A transpose times a vector is always 0, that means that the matrix A transpose times that vector should be the 0 vector. Again, what we're saying is you take any row of A transpose and multiply it by this vector right here, it should be 0. Therefore, the product of the matrix A transpose times this vector B minus A x hat should be identically the 0 matrix, or actually technically the 0 vector. So I should not have bolded that. I should have written that with a vector sign above it. Well, what does that mean? Well, if you distribute through and you get A transpose B minus A transpose A x hat is equal to 0, and you move the A transpose A x hat to the other side, you would get the following. That A transpose A x hat is equal to A transpose B. Now, what the heck does that mean? I mean, didn't we already know that if AX equals B, then A transpose times A times X should equal A transpose B? Well, yeah, we know that. But if X hat is the solution to this equation right here, AX hat is equal to the projection of B onto the column space of A, then X hat is also a solution to that equation A transpose A times X is equal to A transpose B. And that's significantly important and helpful in what we want to do. And remember, that equation is called the normal equation, or it's often pluralized, the normal equations. This theorem right here allows us to use that result in a really convenient way. So let's read the theorem first, then in the proof, we're going to have to use the result that we just wrote down. The set of least squares solutions of AX equals B coincides with the non-empty set of solutions of the normal equations. So this means that if I want to find the least squares solution to AX equals B, I could instead solve A transpose A x hat is equal to A transpose B. And I actually think it's going to be very helpful to use this theorem before we come back and prove it. So let's go ahead and find the least squares solution for AX equals B, where A is this matrix right here, and B is the vector 2, 2, negative 1. Now, just to remind you, we actually found the least squares solution to this in the previous video. It was this guy right here, and the solution ended up being negative 16 over 41 and 3/5. But let's go ahead and use our new theorem to see if we get to the same solution. Now, the new theorem tells us if we want to find the least squares solution of this, well, all we need to do is solve A transpose A x hat is equal to A transpose B. And by the way, in a textbook, your author might not write this as A transpose A x hat is equal to A transpose B. They may just say solve A transpose A x is equal to A transpose B. I use x hat here because it's traditional to use x hat when you're finding least squares solutions. So I just kind of note it that way no matter what. Our first task here is to find out what is A transpose times A, and then we'll find out what A transpose times B is. So there's A right there. Let's go ahead and find out what A transpose times A is. Now those numbers should look hauntingly familiar to you if you've been watching my video lectures. And notice this matrix ends up being a diagonal matrix. And that's true because and only because the columns of A are orthogonal to one another. They did not need to be orthogonal to one another for this process to work out the way it's going to work out. However, if your columns of A are not orthogonal to each other, then you will not have this nice, clean, beautiful, sparse diagonal matrix. Such is life. What are you going to do about that, right? So, all right, A transpose times B. Great, we get there. Now to solve A transpose A times X hat is equal to A transpose B. We'll place those in an augmented matrix, even though honestly, there's not a lot of need to do that in this specific case, but let's just go ahead and do it. And we get down to the same answer we had before. This right here is x hat. It's a vector you would multiply against A to arrive at your projection of B onto the column space of A. And I want to be very clear about that because this often confuses people. Well, I shouldn't say often, it's every once in a while it gets confusing to people. You're dealing with two things here. The projection of the vector B onto your column space of A, or in other words, the shadow of that vector B onto your column space of A. And then you're solving a system that's equal to, where the right-hand side is equal to that shadow vector. And you're really trying to find that x hat. What is the solution to the system, the alternate system that's looking for the right-hand side to be that shadow vector? So that's this solution right here. The entire time, we know there's actually no solution to ax equals b because we've already tested this system before and found out it's inconsistent. I should also mention here, some people will ask, wait, what if, for example, b is in the column space of A? Well, if b is in the column space of A, then the projection of b onto the column space of A is the actual vector b itself. This process still works, but you're doing more work than you need to when you solve using this process, so don't. Now, I decided to go ahead and move forward and do another example before hopping back to the proof of the theorem that we're currently using, just because I want us to get used to using this theorem. So the following example illustrates why we use the plural form when speaking of the normal equations. Remember, the normal equations are A transpose A times x hat is equal to A transpose B. So you're working on a big project, somebody says, man, I know that this system is inconsistent. Ax equals b has no solution. And by the way, you can test this out if you want to. It actually does not have a solution. So you're more interested in the least squares solution, the minimized error solution, if you will. And now that we know that the least squares solution to ax equals b coincides with the solution of the normal equations, we're going to go ahead and solve the normal equations. To do so, we'll need to find A transpose A and A transpose B. So let's go ahead and do that. Now, something I want to mention before I continue forward, you probably have already noticed this, or maybe we've proven this somewhere in this course. I cannot actually remember, but when you multiply a matrix A, specifically a square matrix, A transpose times itself, well, the diagonal is going to be the sum of the squares of the corresponding product. That is, the diagonal element in row 1, column 1 is actually row 1 of A transpose times column 1 of A transpose, which is actually just row 1 of A transpose dotted with itself. So it's going to be 3. And row 2, column 2 of the result is just going to be row 2 of A transpose dotted with itself, 0 plus 1 plus 4. And if you take row 3 and dot it with itself, that's 1 plus 1 plus 9, which is 11, and that ends up being the third diagonal element. So that quickly gets us these 3. Now, using basic matrix operations, you can find out what the first row second column entry is by multiplying the first row of A transpose by the second column of A itself. When you do that, you get 0 plus 1 plus 2. Not a big deal, but it's symmetric. Because it's A transpose times itself, it'll be symmetric. Notice -3, -3, -7, -7. So you can take advantage of the symmetry of A transpose times A to really speed up your computation. In fact, that is often done in algorithms coded into computer programs. All right, now let's find out what A transpose times B is. That should actually be very quick because you're just taking this matrix right here and multiplying it against the vector 6, 0, 0. So it's just going to take 6 times the first column. All right, let's solve that system of equations. And notice that we only have 2 pivot columns. We have a free variable in this system. Therefore, there's an infinite number of solutions to the corresponding system. Hence, our least squares solution to ax equals b is not just one vector. there are actually an infinite number of vectors in the column space of A that will minimize the distance between the vector B and the plane, which consists, or I should say the subspace, which is the column space of A. So that can happen. That's why you have a plural on the normal equations, and also actually on the statement that you have a least squares solution. Notice I've been asking find a least squares solution, not the least squares solution, because saying find the least squares solutions implies that there's only one, but that's not always the case. There could be an infinite number of them. It could be the case that your vector B is just as close to one point in your subspace as it is to an infinite number of other points in that same subspace. Anyhow, we found a least square solution. In fact, we found an infinite number of them. So if you let x sub 3 be 0, well then one solution would be 5, negative 3, 0. If you let x sub 3 equal 1, then that least squares solution would be 4, negative 1, 1. And if you let x sub 3 be something else, right, you keep adjusting that. Now that all being said, let's go ahead and hop back to the theorem itself and ask ourselves, why is this true? Why is it the case that the set of least square solutions to ax equals b coincides with the non-empty set of solutions of the equation A transpose A x hat is equal to A transpose B? Well, this is actually an if and only if. It's just not written that way, but it technically is an if and only if. We're saying that if x hat is a least square solution of ax equals b, then A transpose A times x hat must equal A transpose B. Likewise, we're saying that if A transpose A x hat is equal to A transpose B, then x hat must be a least square solution for ax equals b. Now you might say, hold on a second, that can't be true, because if A transpose A times x hat is equal to A transpose B, then A x hat must be equal to B. That's actually not true. That's not true at all. We happen to know, if we start with the assumption that this is inconsistent, ax equals b, we know there's not a solution to this. However, if I modify the equation and I can get a solution, we'll call that solution x hat. And if that equation right there, which is a different equation, has a solution, well, it will also be a least square solution for ax equals b. But just walking in the room and saying, oh, A transpose AX equals A transpose B implies AX hat is equal to B is not actually true. A transpose would have to be invertible for that to be true, and therefore A would have to be invertible. Anyhow, let's just dive into the proof. We're going to prove it both directions. We'll go forward first, so let's go ahead and assume that x hat is a least square solution for AX equals B. And like I said, we're going to prove it forward first. So consider the set of least square solutions of ax equals b. Well, these are all the x values in our n, and we're going to call those x values x hat, such that the distance between ax hat and the vector b is minimized. Now I'm kind of recapping the definition of a least square solution here, just for your benefit. And in our proof, we're going to use this theorem right here, which is called the best approximation theorem, which tells us that the best approximation, or the closest point to y, is going to be the projection of our vector y onto the column space of A. That is, by the best approximation theorem, this occurs precisely when this vector A times x hat is actually the projection of B onto the column space of A. Again, just recapping stuff that I've said earlier. But what's important about that is that the projection of B onto the column space of A is actually a vector in the column space of A, right? It's a projection of B onto the column space of A, so it must be in the column space of A, which means that the matrix equation A times some vector equals the projection of B onto the column space of A must have a solution, because that right-hand side vector is in the column space of A. So that equation is consistent. Now that we know that equation's consistent, we can go back to our previous very first page, or second page in this video, I think is what it was, where we said, well, if x hat satisfies that A x hat is equal to the projection of B onto the column space of A, then A transpose A times X hat must be A transpose B. That's why I made mention of this early on, so that we could use it here. We happen to know that A times X hat is the projection of B onto the column space of A, and by that statement we just reminded ourselves of, that implies that A transpose A times X hat must equal A transpose B. What does that mean? Well, that means that if X hat is a least squares solution for AX equals B, then A transpose A times X hat must equal A transpose B, which is exactly what we're trying to show forward here. So we've gone from left to right. And by the way, I summarized that right here. Hence, a solution to the least squares problem is also a solution to the normal equation. Now let's go ahead and prove it the other way. We'll assume that A transpose A times X hat is equal to A transpose B, and we'll want to arrive at the fact that that will imply X hat must be a least squares solution to AX equals B. That's actually a really cool proof so far. So going backwards, now assume X hat satisfies the normal equation A transpose A X hat is equal to A transpose B. So again, starting on the right hand side here, we'll want to arrive at X hat B is a least squares solution for AX equals B. Well, if that first statement right there is true, I can shove everything over to the left-hand side and factor out A transpose, and I get to that. And again, as I mentioned previously, this should be a vector on the right-hand side, but we've also mentioned something before. A transpose times this vector always being the zero vector means that all the rows of A transpose are orthogonal to the vector B minus AX hat. And that's what we're going to state right here. The vector B minus AX hat must be orthogonal to all the rows of A transpose. Hence, B minus AX hat is orthogonal to all the columns of the matrix A. What does that mean? It means that that vector B minus AX hat is not in the column space of A. Specifically, it's orthogonal to all vectors in the column space of A. So let's see, how do we arrive here? And we haven't really ended yet, but I just want to recap. So we are assuming that X hat satisfies the normal equation, and then we shoved everything over to the left-hand side, and we found out, oh, that just means that every row of A transpose is orthogonal to this vector B minus AX hat, which means that every column of A is orthogonal to the vector B minus AX hat, which means that B minus AX hat is orthogonal to all vectors in the column space of A. So the vector B can be represented as AX hat, which is a vector in the column space of A, plus B minus AX hat, which is a vector orthogonal to the column space of A. This is the orthogonal decomposition of B into the sum of a vector in the column space of A and a vector orthogonal to the column space of A. However, orthogonal decompositions are unique. So if you're going to say, well, isn't there another decomposition of B into those orthogonal vectors? The answer to that is no. Orthogonal decompositions are unique. So since orthogonal decompositions are unique, AX hat must be the orthogonal projection of B onto the column space of A. Again, that's because AX hat is in the column space of A, and it's the orthogonal projection of B onto that column space of A because it's the shadow of B onto that subspace. And every vector can be written as the sum of two vectors, one of which is in your subspace and the other is orthogonal to your subspace. Or maybe I should say one of which is the orthogonal projection onto your subspace and the other is orthogonal to that orthogonal projection. That means that X hat is a least squares solution of AX equals B, because look at this equation right here. That's exactly what the least squares solution is, right? It's when you solve AX hat is equal to the projection of B onto the column space of A. So therefore X hat must be a solution of that equation. That is, X hat must be a least squares solution for AX equals B. That's very convoluted. I don't mind if you are a little bit confused by that, but just watch it a few times. It might start clicking. it is a little bit of a tough pill to swallow. Luckily, that's the last thing I'm going to do in this video. So again, rewind a little bit if you need to kind of review that proof. It is actually a really nice, clean, elegant proof. It has a lot of the theory that we've gone through so far in least squares and orthogonality. Well, I hope to see you in the next video, which is going to be all about the uniqueness of least squares solutions and the error that you can get with least squares solutions. And I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just